Everyone. Welcome to the second episode of the simulation effect. Today, we will discuss a workflow on Ansys InterConnect about characterizing a continuous variable quantum key distribution photonic integrated circuit. My name is Paschalis Doboudis. I've been working as an optics and photonics application engineer in SimTech for the past 2.5 years. I hold a bachelor's degree in physics, and I'm now completing my master's on quantum computing and quantum technologies. So let's begin. So let's start with the why. Quantum computers aren't science fiction anymore. Labs worldwide are scaling them up faster than many of us expected. Once they reach a certain size, today's public key cryptography will collapse. The main culprit is source algorithm. It turns problems we rely on, such as factoring big numbers and solving discrete logarithms, from practically impossible into easy. So that instantly breaks some cryptography protocols such as RSA, Diffie-Hellman, elliptic curve schemes, and DSA. And even our symmetric systems are at risk. Grover's algorithm doesn't destroy them outright, but it does give a quadratic speedup to brute force attacks. So in plain terms, a 256-bit hash only behaves like a 128-bit hash against a quantum attacker. So the industry now talks about Q-Day, which is the moment the cryptographically relevant quantum computer goes online. So from that day forward, anything still protected by classical keys can be decrypted. So that's why we need quantum safe or post-quantum keys and protocols, and why the rest of today's talk focuses on designing and validating them. Here is an overview of quantum key distribution. We can imagine Alice, which is the transmitter, and Bob, the receiver, that are linked by two channels. We have a quantum one that you can think as individual photons traveling down a fiber, and a normal classical channel like the internet, but authenticated so nobody can read our messages. First, Alice sends quantum states that encode random bits. Because quantum states cannot be copied without disturbing them, any eavesdropper will leave noise. Bob measures those states, and now both parties have a long string of bits. And next comes the public chat through the classical channel. They reveal just enough information to spot where their settings matched. All mismatched or uncertain bits get tossed out. So this process is called shifting. The strings of bits will still contain a few errors, so they run an error correction protocol to align every bit. And finally, they apply privacy amplification to squeeze out any information an eavesdropper might have learned. Now, the quantum key distribution family comes in two main categories, and the difference is right there in the names. We have discrete versus continuous variables. With discrete variables, Alice fires individual photons down the quantum channel. Each photon carries a yes or no bit, 1 or 0, which is encoded, for example, in the polarization of the photon. Bob's job is to spot that photon with a single photon detector. If his measurement basis matches Alice's encoding, they keep the bit, otherwise it's discarded. In continuous variable QKD, Alice sends very faint laser pulses instead of single photons. She tweaks each pulse's amplitude and phase, which are two values called the quadratures. And Bob mixes the light with his own laser, and using standard telecom receivers, reads those two numbers. To put it simply, discrete variables is like Morse code, dot or dash, 0 or 1. Which makes it robust even when the signal is faint. Continuous variable is more like an analog dial. So it's smooth, it has a high bandwidth, but it hates noise. It's more prone to noise. So before we dive into the simulation, we need to understand the principles of continuous variable QKD. which is the coherent state. If you picture the electric field of a laser as an arrow rotating in the complex plane, the arrow's horizontal projection is the Q quadrature, and the vertical projection is P. So if we put those numbers together, we get a single complex value, which is A plus IP. A equals Q plus IP. So that pair can completely specify a coherent state. So what makes coherent state special? They look almost classical. So its noise, the noise of the coherent state, is as low as quantum mechanics allows us. And it evolves in time just like a classical wave. And second, we can change Q and P smoothly and independently, which is perfect for encoding information. Now, Alice uses a method in our example called Gaussian modulation in order to sample the two quadrature values. So she starts by randomly picking two real numbers, one for the in-phase quadrature called Q, and one for the out-of-phase quadrature called P. So these numbers follow a Gaussian distribution that is centered on 0. So over many rounds, the states Alice sends form a fuzzy cloud around the origin of phase space. We will see an example of that later. So these values set the coherent state amplitude, as I said in the previous slide, Q plus IP. The size of this cloud is governed by the modulation variance, which is an important parameter. We label it as V sub mod. And choosing the right value is very important because it affects how much the secret, it affects the secret key rate. Now, at the heart of any continuous variable QKD is the choice of homodyne or heterodyne detection. Homodyne detection is simpler in concept. You tune a local oscillator to match the signal's optical frequency and measure just one quadrature each time, so either Q or P. This method adds no extra noise beyond what's in the channel or your detector. In the heterodyne protocol, we try to read both quadratures at once. So that means that we have to split the incoming pulse and combine it with a slightly offset local oscillator or using a special 90 degrees optical hybrid. The trade-off is that due to quantum mechanics, measuring both at the same time injects an extra unit of noise. The upside is that heterodyne gives you two real numbers per pulse, so instead of one, which means that with this detection method, we can double the key rate. Here we can also see some critical parameters to assessing the security of a quantum variable QKD system. First, we have T for transmission, which is the fraction of optical power that reaches Bob. So if T is low, that means that we have high loss, which can be due to fiber attenuation, poor coupling, or even an eavesdropper siphoning off photons. Then we have Xi, the excess noise. This is the most important security parameter. If noise beyond the expected shot noise level appears, it might be from technical imperfections, or it could indicate if is tampering with the quantum signals. The next parameter is beta, the reconciliation efficiency. It tells us how effectively Alice and Bob can correct their errors without leaking too much information. And lastly, V accounts for finite size effects. In real-world systems, we only exchange a limited number of quantum states. That statistical limitation introduces uncertainty in how well we can estimate the channel's behavior. So together, these four parameters are essential inputs to any secure key rate calculation. Then we have the shot noise units. In order to judge the performance of our QKD system, we need a reference, which we call a shot noise unit. The shot noise is the tiny and unavoidable noise that even an ideal laser pulse picks up. So its variance sets the fundamental noise floor allowed by quantum mechanics. the way we measure it is that in 3 steps. Step 1 is that we have both the signal and the local oscillator beams blocked. We will see the example in interconnect later. We have both beams blocked. We record what the detector electronics alone contribute. So that's our electronics noise. Then we unblock only the local oscillator of Bob, and the detector now sees the vacuum fluctuations caused by the local oscillator and the electronics. So the final step is to subtract these 2 noises, let's say, and the difference is the clearance that we use as one shot noise unit. So the reason we care so much is because every other quantity, such as Alice's modulation, Bob's measurement noise, and the excess noise parameter must be expressed in shot noise units. There is also an attack that could, let's say, there is a way that an eavesdropper, let's say, could trick us into miscalibrating this scale. So they could hide extra noise in plain sight, meaning that they could trick us into believing that our exchange is secure when it is not. So we have to make sure that this calibration goes well. And everything we discussed so far, loss, noise, reconciliation, end up in this one expression that tells us how many truly secret bits per second we can deliver. We will analyze this equation later. Now, finally, before the simulation, we also use, in our example, we also use another concept that is called pilot-assisted quantum key distribution. First, let's start with the problem that this concept solves. Bob has his own laser, the local oscillator, that he uses as a reference clock. Unfortunately, Bob's laser and Alice's laser never stay perfectly in step, and thus they drift in frequency and phase by time. So if we do nothing, that drift destroys, let's say, the quantum signals and introduces a lot of noise. So the fix is that alongside each weak quantum pulse, Alice sends a much stronger narrow band pilot tone on the same fiber, the same quantum channel. So at his end, Bob measures both the pilot and the quantum pulses at the same time. And because the pilot is, let's say, bright and clean, Bob can easily see how far his own laser has drifted from Alice. So his digital signal processing chip then rotates every quantum data point back into perfect alignment. For our example, for our simulation, we used Lumerical INTERCONNECT. INTERCONNECT is a design environment for building and testing photonic circuits, similar to how you design electronic circuits. So it uses a schematic editor. You can easily put together complex systems by dragging and dropping components onto a canvas, let's say. So one big advantage is that it can handle multiple technologies at once. So you can model optical and electrical parts, which we will also use in our example, together. And you can also include thermal effects if needed. Interconnect also comes with a large library of ready-made parts. So we have a library with waveguides, lasers, modulators, detectors, filters, multiplexers, etc. And finally, when it comes to simulation, you can run time domain and frequency domain analysis. You can check signal quality. You can run statistical tests like Monte Carlo. And after the simulation, you can also create some plots like eye diagrams, bit error rate curves, or spectra, etc. So here we have the whole continuous variable QKD link in one picture inside interconnect. It is broken into 3 color-coded regions. First, we have Alice in red. We will discuss each part in the later slides. In green, we have the channel, which essentially is just the fiber. And then in blue, we have Bob, which is the receiver. Now, let's zoom into Alice's block first, Alice's circuit. First, everything begins with a single frequency laser. This is the laser that creates the quantum signal that will be sent through the fiber. Second, we need random numbers. So we have two pseudo-random bit streams that feed the I and Q modulators. So after some shaping, they become the Q and P values that are sampled through our Gaussian distribution. Third, we generate a separate pilot tone, which is essentially a pure sine wave at radio frequency, 1 gigahertz. Fourth, we have the pilot Mach-Center modulation that imprints the pilot tone onto the laser with a very small depth. Fifth, we have the dual drive IQ modulators that convert those random numbers into the amplitude and phase and produce the weak coherent states, which are the actual quantum signals that will carry the key. Then we have a pair of phase shifters that keeps the two arms in perfect quadrature, so the constellation is truly Gaussian. And finally, a polarization rotator that will turn the pilot's polarization by 90 degrees. So now the pilot and the quantum signal share the same fiber, but stay in orthogonal polarizations, which let Bob separate them cleanly afterwards when he receives the signal. Here we can see everything between the Alice and Bob box circuit, which is the quantum channel. The most important thing here is the fiber that you can see in the middle. So this is the quantum channel, which is 13 kilometers in our example. Now this is the circuit of Bob. First, we have the local laser, the local oscillator that we discussed previously. Then we have the optical hybrids, which are 90 degrees optical hybrids that mixes the local oscillator with the incoming signal and spits out 4 copies that are 90 degrees apart. Then we have balanced photodiodes. So each optical pair hits a balanced photodiode that converts the optical signal to an electrical one. And then by subtracting the two diode currents, we keep the quantum information and cancel a big chunk of the local oscillator's noise. Then we have transimpedance amplifiers that boost those tiny difference currents into RF voltages. And then the 4 paths hit a pair of filters. First, we have the low-pass filters. These are used to block the pilot signal and keep the quantum signals. That's why they are low pass. And then we have the narrow band pass that isolates the pilot tone, so we can track and correct the laser phase and frequency in real time. And finally, we have the digital signal processing part, which we will see in the later slides. So we saw the circuit in interconnect. Now we have to perform some steps in order to extract the parameters needed for the calculation of the secret key rate. So the first step is the important step of noise calibration. First, we measure the electronics alone, as I said in the previous slides. So we block every light path. We have no signal and no local oscillator. And what's left is the tiny hiss of the receiver electronics. Then we still don't have quantum signal in step 2, but we turn Bob's laser up to about 16 milliwatts. So now the photodiodes will see the unavoidable noise due to the local oscillator. Step 3, we subtract the electronics variance from the local oscillator on variance, and that difference is one shot noise unit. Then we repeat this loop 8 times with different random seeds, and we take the average just to be sure that the value is stable. And final step is also to check the clearance. The clearance is the ratio of the electronics, the local oscillator plus electronics to the electronics noise. So in decibels, that should be at least 10. Otherwise, the electronics would mask the quantum signal and weaken security. So here are the numbers from our calibration run. The blue trace is with Bob's local oscillator on. The green trace is with it off. So the vertical gap between them at average is almost 19 decibels. And this is what we call the shot noise clearance. Anything, as I said previously, anything above 10 decibels is considered safe. And the table shows also the variance we extracted. We get essentially the same value on the I and Q quadratures, so the detector is well balanced. Next step is the signal simulation. So with our detectors calibrated, we now let some real quantum traffic flow and measure how well the link performs. First, Alice sends thousands of weak coherent states plus the bright pilot tone. Bob mixes everything with his local oscillator and captures the raw I and Q waveforms. Second, we read the pilot tone to see exactly how far Bob's laser has drifted, and we digitally rotate every data point by that angle, which straightens the constellation into a circular cloud. We will see the plots in the next slide. Then all those points are scaled by the shot noise unit that we measured earlier. Then the fourth step is to compare Alice's original simple values to Bob's corrected ones in order to find the transmittance. Fifth step is to combine the transmittance with Alice's modulation depth to get a signal to noise ratio. Sixth step, we measure the total variance of Bob's data, subtract off his own detector noise, and what's left is the excess noise, Xi. And finally, we repeat the whole sequence several times with fresh data, and we average the results to give us a smooth spectra and stable constellation plots. So here are the plots, the results from the previous steps I described. The top left plot, the blue trace is the pilot's accumulated phase. We can see that in over just 20 microseconds, Bob's laser has drifted at about 1.5 rads. The top right is the corresponding spectrum that confirms that the pilot is a clean single sideband tone sitting at 1 gigahertz. You can see that you can see the peak that is formed in 1 gigahertz frequency. The middle row on the left, we have the pilot samples that form a donut. This is due to the phase drift. After the digital signal processing rotation, we have the right plot where every point lines up on a single diagonal. And the same we can see in the bottom row, but on the quantum data, not the pilot. So the same correction is applied to the quantum data. Before rotation, you can see the four color-coded symbol families that are stretched into an ellipse. After the rotation, we can see that the cloud has centered around 0. And here we can see other extracted parameters. We have the modulation variance, which is 3.7, the transmissivity, which is 0.42, the SNR 0.78, and the excess noise Xi, which is 0.033 shot noise units. So everything ends here. We combine the physical measurements with the constants, the protocol constants, and obtain a single number k, which is the secure key rate in bits per second. So from the preceding steps, we know the modulation variance, we know V mod, we know the channel transmittance, we know the trusted excess noise Xi and the SNR. And the protocol fixes the reconciliation efficiency at 0.97. We also have the fraction of symbols revealed for parameter estimation. This is V, 0.25. The frame error rate is at 0.05. And we also have the 250 megahertz symbol rate. Then we have some maths. I will not tire you with the math so much. First of all, we have three physical parameters, V mod, transmissivity, and Xi, and we can define a Gaussian covariance matrix from them. And in compact form, it depends. This matrix depends on three scalars. We have A, which you can see how we can calculate the B and C. Now diagonalizing that matrix will give us two global eigenvalues. We have V1 and V2, which can describe, let's say, the joint Alice and Bob state. And we also have a third eigenvalue, V3, that describes Bob's state after the heterodyne detection. Then if we substitute these three eigenvalues into the von Neumann entropy formula, we get the Holevo bound, X EB, which is Eve's optimum knowledge per pulse. Then we have Alice and Bob mutual information. So due to the Gaussian statistics, the mutual information per pulse is exactly log 2 of 1 plus SNR. So if we multiply this by beta, we can account for the real world efficiency of the decoder. And finally, the final step is to use all these values, these calculated values, to calculate the key rate. This formula is also called the Devitag-Winter formula. So essentially, what we do is that we subtract the Holevo bound from beta times IAB, and then we scale by three factors. We have the pulse rate, the fraction of frames that decode cleanly, and then the fraction of symbols we did not reveal for parameter estimation. And the product of this formula is the key rate. So if we would like to interpret this formula, so if that bracket here ever turns negative, the protocol actually halts, because Eve could know more than Bob. When it's positive, multiplying by the values that we already know about the parameters, we calculate 38 megabit per second key rate over the 13 kilometers of our fiber. This figure also shows a small parameter sweep I did of the fiber length, and we can see the impact on the secret key rate in our QKD system. So it is obvious that as the fiber length increases, the secret key rate decreases significantly. And the last slide contains some concepts about QKD that I find interesting, and I hope you also find them interesting too. We have free space, QKD, which are continuous variable protocols that transmit the coherent states through atmospheric links. We also have satellite QKD, which are quantum keys that are generated by orbiting satellites. And this is also the backbone of future global quantum networks, if they will ever exist. Then we also have airborne and drone-based QKD, where we use drones or aircrafts for mobile quantum nodes, and then some attacks that we could perform in order to decrease, let's say, the security of the quantum key distribution systems. We have photon number splitting attack, the blinding attacks, time shift attacks, channel amplification attacks, and the Trojan horse attacks. So thank you everyone for being here. The simulation effect will continue next week with the episode Material Intelligence in R&D using Ansys Granta. Have a nice week.